Hi everyone, welcome to Python tutorials where we are focusing on image processing related tasks. And we have been discussing about various terminology for deep learning, especially in the last dozen videos. And now let's start to put that knowledge into some action. Now in this video, let's look at the 7 steps to build our deep learning model. And these are the steps that you typically have to verify before getting into any deep learning related project. I mean, these are very intuitive steps. So as you will see, it involves understanding your data. It involves putting together your model and so on. But if you look at these 7 steps and say, okay, I've done this, I've done that, it gives you a nice framework to follow in terms of building or approaching your project that you're trying to solve using deep learning. So let's quickly look at, what steps are involved, and then we'll summarize the steps in a minute, and then we'll jump into the code to actually put together a solution using deep learning by following these steps accordingly. Okay. First of all, it's again, this may sound like common sense, but we often jump into solving a problem without trying to fully understanding the problem itself. So it's very important. So you have to understand the data and the problem to be solved, because even before you write any lines of code, you will know right away whether it is solvable, not solvable. Do you have all the data? Do you need to get more data, and all that? So here in this case, this is again the breast cancer data set. We have malignant and benign, and we have, for example, 200 of these representing malignant and 350 data points representing benign. So when you plot it, it gets very visual, and now you can decide whether you would like to use any of the data balancing techniques. We talked about this again, right? I mean, we in the one of the previous videos. Do we need to balance this? Okay, that's one decision you have to make. And the other thing is you look at the data itself. How is it spread? What are the values, and how many data points do you have? So all of this is very important. And the next step is looking at any relationships between the attributes that you have. Okay, for image classification, that's a different topic, but for structured data, which is what we are looking at here, we are given a lot of attributes or features, and one of the features is radius, and the other one is perimeter, the other one is area. Apparently these are all independently measured. It's not like area got calculated from radius. It appears that, otherwise it would be a perfect curve or a perfect straight line here. So here I just plotted radius versus perimeter, radius versus area. Obviously radius and perimeter are related in a linear way. Radius and area are related in a square relationship. But then if you look at radius and smoothness, I don't see much of a relationship between these two, right? And why am I doing that? Because when you're training a machine learning model, you have to make sure your features that you're feeding this machine learning model, whether it is deep learning or not, they are typically independent. If they are dependent variables, you're not giving any new information to the algorithm, right? I mean, to your model. So maybe we don't even need the area and perimeter in this case, and you may have quite a few of these relationships. So this not only makes your model much faster, but it also improves the accuracy of your model. And again, it completely depends upon the problem. So this is one of the things that you need to understand. And also, again, we are still looking at the data. The actual machine learning part is the easy part. So here again, I'm looking at, okay, what values do I have for radius? Radius is like about 14 in this case, and my perimeter is about 91 or something, which makes sense. You just multiply that with 2 pi, you get your perimeter typically. So it's about an order of magnitude higher than radius. If you look at area, this is 2 orders of magnitude higher than radius. But in this case, we have decided that perimeter and area, we are going to drop them, right? So, but let's look at concavity. This is 100th of, all I'm saying is, look at the range. This is 1000th, 100th, and this is like 14, like tens. So there is a difference in the order of magnitude. So again, we know what to do in this case. Scale your values all the time. So you have to decide whether you need to scale it, whether you need to normalize the values. If scaling, which one? Is it min-max scalar, standard scalar? So typically min-max scalar works great. Okay, so this is another decision. Now, of course, define and pick a model. Don't make your model too complex. In these type of structured data sets, it's typically the simpler the model, the better it is. Unless this simple model is not solving your problem, meaning you're not getting anything above 90-95% accuracy, and you would like to push and then get even better accuracy. But always remember to store at least 20% of your input data as your validation data, so you can validate the model while you're training it. And if you're not getting good accuracy, go ahead and change it. Go ahead and add another dense layer, dropout, and then batch normalizations and all the stuff that we learned in the past few videos. And of course, how would you evaluate it? Of course, you're going to plot your training loss and validation loss, accuracies, and then see whether you're getting accuracies close to what you're looking for that problem, and is the problem converging or is it still jumping up and down. Again, watch the video about how to interpret these training curves. That should help you in figuring out how good your model is. Of course, again, go ahead and print out the confusion matrix to see, are you actually doing better on one class compared to the other class? In this case, this is a great result, as you can see. But sometimes you see that, okay, you're doing great on one, but then not on the other. So if so, does data augmentation actually help? Like, what tools do you have to kind of make this better? So these are the things you have to think about while building your deep learning model. And so all of this, I just summarized this to 7 steps that I intuitively follow. Step 1 is, of course, you have to load the data and understand the problem to be solved. I kept load the data. I included this, which sounds like, okay, yeah, how else are you going to get the data? This can be also a bit challenging. Sometimes your data comes in a CSV file. Sometimes your data comes in individual folders saying, okay, this folder has all images of cats, and this one dogs, and this one, something else and something. That would be the best way. Then you have all the images and the labels that you can read from the folder names, right? Oftentimes you have a folder that has 10,000 images, but then a CSV file that has image name and then what class, or whatever the label is. These can be a bit challenging because then you have to load your CSV and then look at what images you have and then sort them and potentially put them in subfolders if you would like to use data generators and so on. So loading data is may sound simple and straightforward, but depending on how the data is organized, you may have to follow various paths to get the data to the model. And understand the problem to be solved. So this is one. I focus most of the time. In fact, this takes a lot of time. And the second step also takes quite a bit of a time. Cleaning up and pre-processing the data. This means remove null. If you have a CSV file, some entries are missing. How do you handle that? You have to fix that first. Or do you need to extract features if they're not provided? Meaning if you have a bunch of images and you're doing traditional machine learning, or even, especially traditional machine learning, we extracted features. Or if it is structured data, no features are provided, you may have to do some feature engineering. Meaning, okay, you have attribute 1, attribute 2. Can you actually mix them, unmix them, in a linear way or in any other way? So that's a separate field by itself called feature engineering. Typically for image analysis, we don't need to do much of any of that, so relax. So, but this is another step that you may have to think about depending on the problem you're trying to solve. Select or drop appropriate features. We talked about this. I mean, area and perimeter, they're kind of dependent. We don't need that. And if patient ID, is associated with certain images, you don't need ID, patient ID, right? So you need to drop that because that has nothing to do with the model itself. And do you need to balance the classes? Do you need to scale? So all of this comes into pre-processing. And the next step is pretty straightforward. Get data ready for training. So you need to split your data into training or testing and validations and so on. Also, at this point, you have to figure out whether you would like to use data augmentation methods, maybe because you have way too much data or too less data, right? I mean, if you have even way too much data, you cannot load everything into your memory. You have to use some sort of data augmentation where you're reading from the folders itself only in batches. Let's say 32 images at a time, and then you're kind of transforming them if you want to, and then feed it. So this is basically getting your data ready for training. You have to think about this. The next step is pretty, again, defining the model. We talked about it. Sometimes you can just take a model off the shelf, like, oh, there is a VGG network, there is a ImageNet, or there is a ResNet, or Inception network. Again, these are all the networks, pre-existing, architectures that people have trained on thousands of images. So maybe you would like to take one off the shelf rather than build one from scratch. So defining the model, again, this is where you need to do some experimentation in terms of what's best for your problem. Unless someone else solved that problem, then you can obviously copy it. Next, training the model. Ensure enough validation data. That's the only point I would like to make when it comes to training the model. Do not underestimate the importance of validation, because this is going to tell you if your model is doing the right job or not. Just imagine if you have thousands of data points where you're saying, okay, so when should I when do you think I win a lottery, right? So you can say, okay, the last few times someone in my family won a lottery, then there was some sort of it was raining in I don't know, it was raining in Ohio. I'm just making some stuff up. Because if you feed lots of data to your model, it will find patterns, whether they make sense or not. You have to be very careful. This is where capturing features or defining features can be very useful. So it's like, okay, so I win a lottery whenever it rains in Ohio. So you look at your forecast and then you purchase, but that obviously that's not going to happen, right? So how do you know that that's not going to happen? This is where validation data comes into picture. Now you take the validation data and apply your model, and the validation is not going to say, typically with very low certainty, it's going to say that's going to happen, right? So that's I hope that makes sense. So validation data, if you have enough validation data, then you can actually ensure that this model is seeing false patterns, because it's doing good on training data but not on validation data. Okay, so it's very important. And retrain if necessary, right? I mean, you train it for 200 epochs and you still see that, oh, I wish I trained this for 100 more, 200 more. Of course you can do that. You continue the training if you haven't closed your session, or you load the model and then continue for another 200 epochs. So either way, you can retrain if necessary, or continue training if necessary. And finally, save the model for future use. That's it. You're all set. Typically, if you follow these steps, I think it's very little that you can actually miss. Obviously, there is something that we may have overlooked here, but this ensures that you checked all the right boxes. So let's jump in and look at an example, jump into the Colab and look at an example we have already looked at a few times in the past, but now with this new framework in our mind. Okay, so let's jump into Colab. Okay, so I'm going to share this link to this file anyway, so please focus on the task here. So again, I copied the 7 steps, and let's go down and go through each step. Again, we are working on this breast cancer Wisconsin dataset that you can download from this link. And here it's got a bunch of columns, a bunch of attributes or features, and a column labeled diagnosis. This is where we're trying to make predictions. Is this benign or malignant? Okay, and all of these other parameters. Now you see there is radius, there is texture, there is perimeter, there is area. So perimeter and area and radius are related. So let's see if we need to drop any of these. But let's go through this step by step. Step 1, what is it? Load data and understand the problem to be solved. So first of all, data includes libraries. Let's load the required libraries, and typically the libraries that you need would be pandas, because you will have to organize your data one way or the other. So I always import pandas. Okay, unless you have very big data, in which case think about Dask, which is similar to pandas, but it's designed to do bigger, larger data sets. That's a separate topic, but for now, pandas is good enough. Matplotlib, because we would like to plot something and then visualize it, and Seaborn also for plotting, but in a much better, easier way. NumPy is helps us work with arrays. So these are essential no matter what work you do. And then let's go ahead and capture our CSV file. into a data frame. Again, I loaded this CSV file onto my Google Drive, and I linked my Google Drive here, by clicking that icon. We already went through this in the past, but just mentioning in case you missed that. So now we have our data frame. So let's go ahead and print the column names of our data frame, just to get familiar with this. So our column names are, the first column is ID. This must be the patient ID. The next column is diagnosis. This is what we're trying to predict. And then you have all of these other columns, radius and texture and perimeter and everything else. Okay, now let's go ahead and look at describe. Again, this is another step I do almost immediately just to get a good feel for how the numbers look like. And this is where you can actually get a nice idea. Okay, there are total 569 data points, and the values range from, ID doesn't matter. You're not going to use that for training, but everything else, just have a quick look of what you're dealing with. The next question is, okay, first of all, what am I predicting here, right? I'm predicting diagnosis here. So I'm predicting diagnosis. So how many data points do I have? How many labels are there as part of diagnosis? So if you just go ahead and count plot, this automatically plots based on the unique values that you have as part of diagnosis. First of all, the values are M and B. M stands for malignant, B stands for benign. So we know right away that we cannot use M and B as part of our deep learning, so we have to convert them into 0 and 1. Okay, so that's something we have to do at some point. So again, we are getting familiar with the data right now. Let's keep going down. Now let's have a look at a few of these distribution plots, like histogram plots of radius, area, and smoothness. So here is the radius, here is the area, and there you go, the smoothness values. Again, why am I doing that? Just to have a quick look at, okay, where is my mean here? About 13, 14. Here it's about 500. Here it's about 0.006 or 007. Okay, so I need to do something in terms of scaling them. Again, look for correlations. I already talked about this as part of the PowerPoint presentation, but since I'm going to give you the code, I may as well explain what each line in this code actually does. I think we have enough data, so it's taking a few seconds to plot, but again, these are exactly the same plots I showed you earlier. Of course, no surprise here, linear relationship between radius and perimeter, radius and area, so we may as well drop these two but then keep everything else, right? It's not just that I have one radius and one perimeter, right? I have area here, perimeter, radius, mean. Again, I have another radius SE, perimeter SE, area here, another radius, perimeter. So we need to drop all of these, yeah, if you don't want to include that as part of your training. So you can, by the way, instead of plotting individual, you can also look at correlated. Like in pandas, you have dataframe.corr. That kind of gives you the correlation values for all of your columns with itself and with everything else. So what I'm doing here is I'm generating that correlation matrix and then unstacking. Why am I doing that? Because I want to sort this from top to bottom. Like if the value of correlation equals to 1, that means it's 100% correlation. And that only happens if you are looking at correlation of radius and radius, the same values, right? It's 100% correlated. It doesn't, so that's why I'm trying to order them. And then I am going to look at all the values that are not equal to 1, because equal to 1 we know, I just explained. And then go ahead and look at the top 30 of those. So let's go ahead and do that. If you do that, you can see that my radius and perimeter mean are correlated 99.7%. Obviously, that's very high correlation. My perimeter and radius, and my radius and perimeter, obviously, whenever you see radius, perimeter, they're very nicely correlated there. And then radius and area is 98.7% correlated. So this gives you an idea. Okay, these are all very highly correlated. So let's not use them as part of our training. Let's not use what? Let's not use perimeter and area and only use radius. So how do we drop that? Again, the next step is cleanup and pre-processing data. Okay, so in this case, I wrote a couple of lines where I said, okay, if you see area as part of the attribute name, go ahead and drop it. Okay, If you see perimeter as part of attribute name, then go ahead and drop that column. So after this, we should have only radius and no area or perimeter. That's it. So already we dropped some of these. So Y feed data, that's not going to help us make the model any better. Okay, so that's what we are doing as part of cleanup and pre-process, and also check if you have any null. So I don't have any nulls. Nulls means obviously missing values, so you can drop those or you can fill those with something, but I have nothing to take care of here. So we check that. Next, the label of diagnosis is not intuitive enough, so I changed that label to label. Again, this is optional step, but good practice to do. Okay, so now we change that to label is an object at this point because it's not a number, it's M or B, right? So we need to change that. That's the next step. So here, what we are trying to do is a bunch of things. First of all, replace categorical values with numbers. That's our goal, right? Change M and B to 0 and 1. So again, we did this in a few of the previous videos, but the key point, let me explain here, is we are using label encoder from scikit-learn, and then we are transforming our malignant and benign into 1 and 0. So label encoder is encoding your labels into 0, 1, 2, 3, 4, and so on, depending on how many labels you have. So here, as you can see, first of all, I'm looking at the distribution of data. I have 357 benigns and 212 malignants. Okay, and now I am converting my B and M into 0 and 1. That's it right here. Okay, a couple of print statements in there. Okay, so again, we are going down methodically. Now we need to take care of our X values. So far we looked at our Y values like labels. Now our X values, they're all over the place. Well, they have 4, 5 orders of difference in magnitude, from 0.0001 to like all the way to 10 or 100. So let's go ahead and normalize or scale the values. So to do that, first of all, let's define our X. You don't want to scale your labels and IDs right now. Let's go ahead and drop label and ID. Again, remember, why am I doing that? Label is our Y, not X. Label is what we're trying to predict. ID is just an ID of the patient. It has nothing to do with my model. So let's go ahead and drop these. So they're all dropped. Okay, label and ID. And the next step is scaling it. Again, I'm printing it just to get a good idea. My radius mean is 14, 19, and here you see 0.003, right? So different orders of magnitude. Let's go ahead and scale them to min and max, meaning it scales the values between the minimum in that data set to the maximum. Okay, and let's go ahead and print it out so we can see that the values are going from 0.0, basically between 0 to 1 in this case. Okay, so now we are done with our pre-processing. Now get the data ready for training. In this example, getting the data ready for training is splitting this into X-train, X-test, and Y-train and Y-test, and I'm separating 25% of my data for validation or for testing. Okay, so let's go ahead and do that. And 426 data points for training, and 143 data points for testing or validation, whatever you want to call it. And we have 24 features or attributes that we are trying to fit. Okay, now let's go ahead and define the model. That's our step number 4. Okay, so again, we are going in a methodical way. Here you can define your import your libraries, or you can do this at the beginning if you already know what you want to import. So I'm using Keras here. Or you can actually do tensorflow.keras.models. I think if you have the latest TensorFlow, even on Colab, you can just do tensorflow.keras.models instead of importing Keras. That's another way. Okay, so from keras.models, let's do sequential, dense, activation, and dropout, because we are going to use sequential method to define our model. And the first layer is going to be dense layer with 16 units or 16 neurons. And I'm going to drop out 20% of those, and my final layer only has 1 output. Why 1? Because this is a binary example. Is this either malignant or benign? And we are using sigmoid, right? it gives us a probability between 0 to 1. If the probability is close to 0, it is, what did we get? If the probability is close to 0, it is benign, right? If the probability is close to 1, it is malignant. So we have to set a threshold to separate these two. We can set it to 50% for now, but we'll get there in a minute. So sigmoid is our activation because this is binary classification. For multi-class classification, it's usually softmax, okay? And what loss function are we going to use? We are going to use binary cross entropy because this is again a binary classification. And let's go ahead and use Adam optimizer. Again, look at the video on optimizers. You know what Adam is, you know, when you watch that video. And the metrics we are going to track here is accuracy. How accurate is it as every epoch goes by? So let's go ahead and print the model summary. And then we'll be ready to train once we have the model summary right there. Okay, so there are total 417 parameters to train. That's not many for deep learning. They should go pretty fast, actually, especially with GPU. And we also talked about callbacks. And I'm not going to save the model after every so many epochs, but you can do that. I commented that part out. The only part that I left is the early stopping. If the model is not going to get, if the model is not getting any better, go ahead and stop with a patience of 3. That means it goes 3 epochs after it finds the best spot, just to make sure that it is the best spot. Okay, so that I'm defining my callbacks. Again, any other callbacks, define them here. And now we can go ahead and train the model. So let us go ahead and do 100 epochs. This is going to be pretty fast, so that's okay. And 64 batch size is okay. It's loading 64 data points at a time. And then training an iteration. And then the next 64, another iteration. And within one epoch, it should see all the data and then moves on to the next epoch. Okay, so let's go ahead and start, and always capture this into some variable. I capture it as history. Then what that does is as part of the history array, it captures all of this data: accuracy, validation loss, and accuracy, validation accuracy. So I can plot it later on. Okay, so there you go. So here it's done. And step number 6 is retrain if necessary. First of all, let's go ahead and plot the loss and accuracy so we can figure out whether we need to retrain or not. So maybe a bit more, right? I mean, for 100 epochs, you see how it's still trying to get to the bottom right there. But if you look at the accuracy, I don't think I can get any better than what I'm getting. Maybe slight improvement if I go 10, 20 more epochs. So if I want, I can go back and then change this to, and then change this to 20. And go ahead and continue. As long as you have the same name like model, it continues where it left off. I haven't exited the program, the runtime or anything, so it's actually continuing. If you plot now, it looks weird because the starting point is different. You see, I mean, now it's zoomed in. That's why it looks bad. But we are just continuing where we left off. Now go ahead and you see, I'm setting a threshold of 0.5. And let's print out a confusion matrix. This is doing an excellent job. And here you can see if you set a threshold of 0.2, how this actually changes. You see, I'm doing very good on true positives, but when it comes to true negatives, the true negative not good, but then a bunch of these are misclassified as 14. So positives we're doing great, but negatives we're not doing great. So the threshold is a good balance between these two. If I go to 0.8, am I doing any better? 0.8 is not bad. You see, a nice balance, but then I am not doing very good on the positives. So this is how you can actually play with your threshold to figure out the right balance. Or again, keep watching these videos. In a couple of videos, we'll talk about binary classification using images, like how we can classify malarial infected and uninfected images into respective bins. And there we'll focus a bit more on how to find the ideal threshold for that specific problem. But there you go. So now you understand that, okay, we are indeed doing a pretty good job. So I'm okay. I can go ahead and I added another training down here so you can continue the training. But once you're happy, go ahead and save the model. That's it. save your model. Why? Well, later on, let's say a month later, I have new data that I need to classify. All I need to do is go ahead and load the model, load your data, and then go ahead and then print out the result. That's it. Okay. So again, please take this as a framework. There may be additional steps, there may be fewer steps depending upon your exact challenge, but at a high level, this can be a great framework. Spend enough time on the first 3 steps, because that really helps you save a lot of effort when it comes down to the bottom 4 or 5 steps down here. Okay. So it's do not underestimate the importance of data handling and pre-processing and cleaning up, and 90% of the time actually goes into that rather than training or putting together your model. Okay, in the next video, let's continue this discussion, but I hope you liked this video, you learned something. Please go ahead and hit the like button, subscribe to this channel, and meet you in the next video.